In this video, we're going to look at general solutions of cos equations and tan equations. And just to remind ourselves, solving trig equations involves determining the angle or the angles which give the required ratio. And if a trig equation has an unrestricted domain for the angle, then there's an infinite number of solutions. And those infinite number of solutions we can generate using patterns that are called general solution patterns. Let's generate some general solutions for cos equations. So following this same idea, if we're looking for solutions for cos of something is equal to some amount, any amount, I've used A here simply because I've got the point A and B, then what we're looking for are points on the unit circle whose x-coordinate is A. And so here's one, so theta is a solution, and here is another point down here. So minus theta is a solution. So we have two solutions already. So we have our two solutions, theta and minus theta. And if we think about what we did last time, every time we travel round 2 pi, we generate another solution based on theta and also based on minus theta. So again, we've got a pattern, 2 pi, 4 pi, 6 pi, they're all plus. From minus theta, if we add 2 pi, we get 2 pi minus theta. So adding 2 pi on here plus 2 pi, swap them around. 2 pi minus theta, 4 pi minus theta, 6 pi minus theta. So now you can see we've got a definite pattern here. And because we're using 2 pi plus theta, 2 pi minus theta, we can combine the two lines together to represent 2 pi plus and minus theta. As a shortcut way of writing the two solutions, we can do the same with 4 pi and theta, 6 pi and theta. So what we've got to generate here are even numbered coefficients for pi. And to get even numbers, we multiply by 2. So we're going to have our counter n again, and this time we're going to multiply our n values by 2. That will give us our even numbers. And again, we need to specify that our counter is integers, and we've combined our plus and minus theta here to make our general solution for cos. All we need to do is find one of the solutions. It doesn't matter whether it's the positive value of theta or the negative value of theta, because this plus and minus will also counteract whether this is positive or negative. So let's have a look at generating some solutions using the general solution formula. I'm going to write a table. Okay, so if we have n at minus 2, we end up with minus 4 pi plus theta minus 4 pi minus theta. So on the unit circle over here, we go minus 4 pi, so that's minus 2 pi minus 4 pi, and then from here we go plus theta and end up in this quadrant here. And if we went from 4 pi minus theta, we continue round again, we end up here. So that green should be back there a little bit. So that puts us in both of our correct quadrants. And you can see that for n is minus 1, we get minus 2 pi plus theta, minus 2 pi minus theta, which again gives us our correct quadrants and correct angles. So all we have to do is find one of those first angles and it works. So in terms of our cos graph, our solutions are 2 pi, which is here, plus theta, and 2 pi minus theta, for our line passing through the y-axis at B. And you can see that that repeats over and over at each multiple of 2 pi. So 2 pi, 0 times 2 pi, you can see that there's plus theta and minus theta. At minus 2 pi, you can see that there's plus theta and minus 2 theta. So you can see the pattern that it's generating the solutions for. Now, if the cos value that we're looking for the angle for is a negative value, then our B is below the x-axis. So when we think in terms of our unit circle, for a point on the unit circle to have a negative A value, that puts it in the second and third quadrant, so over the negative section of the x-axis. And so the angle that we're working with for our solutions for cos of something is equal to minus A are the angle from 0 around to here, which is the angle pi minus theta, or the second angle all the way around to there, which is pi plus theta. So we need to choose one of those two angles as our first angle in our solution. So for the general solution, remember that this theta is one of our first solutions. So we're actually going to replace this for our negative answer with our first solution, pi minus theta, in our general formula. And so it will work something like this. So we had cos of x is equal to minus a half. And so we know our general solution for cos is 2n pi plus or minus. Now we need to figure out one of the values that gives us cos as of minus a half. We know in the first quadrant that if we had cos of pi on 3, we get positive a half. So what we want is pi minus pi on 3 as our value that we add on here. And so our general solution becomes 2n pi plus or minus, and pi minus 3 pi gives us 2 pi on 3. And we will generate our solutions based on this formula with this angle that's in the second quadrant. So in terms of the graph, this looks like, this means that our angles are still using multiples of pi on 2 as their base measurement. So there's all our multiples of pi on 2. But this time they're adding and subtracting a larger amount. You see how it's adding and subtracting a larger amount? And in this case, the amount that it's adding and subtracting is 2 pi on 3, our second quadrant value. So if you're solving a cos function for a negative value, you need to make sure that the angle that you're substituting into your general formula solution is in fact your second quadrant angle. So in this case, we were adding and subtracting each time from the multiple of pi on 2 to pi on 3, which is an angle in the second quadrant. Solutions of tan of something is equal to c or negative c are much simpler. So you can see if our tan value is c, then we're working with angles in the first quadrant and the third quadrant. And so the first angle is theta, and then the second angle from that is plus another pi. So we're doing 180 degrees, it's a straight line, so we're actually adding pi to get our next angle, and then we add pi again to get our following angle, and pi and pi and pi and pi and pi. And that generates all of the solutions that are the angles that give tan of C. If we've got tan of something equal to a negative number, then our answers are down here somewhere. And so we're working with angles in the fourth and the second quadrant. And again, from this angle round to that angle there, 180 degrees, so we're adding pi to get the new value. So the general solution for tan is counting number multiples of pi plus our original value that makes tan of it C or negative C as required. Don't forget, we need to say that this n is one of the integers, one of the numbers that we're using to generate our solutions, just whole numbers. So if we had tan of something is equal to minus C, then we just replace our theta here with minus theta in there. So in summary, solutions of trig equations are angles that exist in at least two quadrants, and they're multiples of those angles unless the domain is restricted in some way. So if the domain's not restricted, there are an infinite number of solutions, and the solutions follow particular patterns. So in a previous video, we looked at solutions of sine, and we had this pattern and another one, which I'll show you in just a sec. And this theta here on the end is kind of our reference angle in our first quadrant, except we need to be careful if we have a negative value of B here, that the angle that we use is negative theta. And the same for cos and tan. They all come with these patterns. They all come with restrictions that can be simplified using the inverse sine functions of inverse sine, inverse cos, and inverse tan. These inverse functions can then be used to write what we call our general solution pattern. And these are our general solutions. These are how they appear in many of the textbooks. Now let me help you read through them. So, if cos of x is equal to a, and that a value has to be between minus 1 and 1, because they're the maximum and minimum values that cos of any angle can have, then the solutions are of the form x is equal to, and this inverse function here will drop out the correct angle that we need. And if you're writing a general solution in an exam, you have to include your definition of the domain for n, what those n values can be, which is always z. For sine of x equal to some value a, that a value has to be between minus 1 and 1. There are two forms of the solution. There's this shorter one, and there's a longer one as well. And you can see in both of these I've replaced theta with that inverse function as well. And again, I've got n is an element of z for both of them. And then finally, the simplest one, tan of x is equal to a. So tan can have any value as its output, and hence a is an element of real numbers here. And our solution again has a counter in it, so we need to define the sorts of functions that our counter can have. In the next video, we'll have a practice at actually using these general solutions.